Okay, this is a new lecture on radical expressions, lecture number 16. You can find it in a Blackboard. So what is this about? Well, radical expressions are any kind of variable expression in which you're going to have radical. And I guess you probably already know what the radical is, but for the sake of precision, we can say this a little more precisely. Radical is, the idea of radical is to reverse the power. So in a unique way. So if you have something like this, you make a square and you get a new number. You make a square of some number, you get a new number. If you want to reverse that, you are going to do something we call a radical or a square root of b, and the result of that is going to be what you started with. There is a little problem here, is that we are assuming that this b is positive, which it is. Of course, when you square any number, you will always get non-negative number. You could get a 0 if you square 0, but you will never get a negative number, so b cannot be negative. That's one assumption. The second assumption, we're also making that a is positive, so the result here is also positive. That might not be the case. Let me give you an example. If you are squaring negative 3, you are going to get 9. If you square negative 3, right? You're going to multiply negative 3 times negative 3, and you will get a 9. So this is your b. But if you take a radical of 9, you could do that. Square root of 9. What number there is whose square 9 is? Now you're probably going to say 3. You're not going to think about negative 3. But we started with negative 3, so this is not entirely correct. If you start with negative 3, you will not get a result here, negative 3. You will get 3. So, to avoid this problem, we're going to say here an absolute value. So now you have no problem. If a is negative 3, the absolute value of negative 3 is 3. So you got to remember that. This is something that you need to be aware of. Looks like I have a little problem with messing up board today. All right. And that is generally the case anytime you have an even power. So if I have an even power, if n is even, I can make a power, and I can make a power to get something new. But when I reverse that, I already know that b is going to be non-negative. If you multiply something an even number of times, I should say even number of factors, but you multiply that like a negative times negative times negative times negative will be positive. You do this with 6 factors, again you will get it positive. So I know that this guy is going to turn out to be positive, so I can do this nth root radical with index n, and I'm going to get the a, but a could be negative, like negative 2, and you make a 4th power, you get 16. Negative 2 times negative 2 times negative 2 times negative 2 is 16. When you make a radical with the 4 as an index of a radical, the result is you not have to think about it. What kind of number there will be that if you multiply that number with itself and you have 4 times that number, like 2 times 2 times 2 times 2, what would that be? Would that be 16? So you're thinking about a number whose product with itself, when you have 4 times that number, you will end up with 16. That, of course, you think about that. The answer is almost certainly going to be 2. But that's not the negative 2 you started with. So I'm starting with an a, I'm ending up with an a, so I have a problem. So I need to, again, change this and call it an absolute value. The absolute value of negative 2 is 2. So, again, this is something you're going to have to pay attention to. So if n is even, we are assuming this guy non-negative. It could be 0, but we are not allowing it to be negative. So it's non-negative, like it could be 0, it could be positive, but not negative. I should probably say it like this. Non-negative. And we also, of course, the result, we are emphasizing that with an absolute value. The result must be also non-negative. The absolute value could never be negative, so I don't need to write that. But this is the condition, right? If you have any other power, what could else be? What could that be? So that you have something else? Well, odd power, right? Then when you have an a with a power of n that is odd to be b, then you can just simply say that the nth root of b will be simply an a. You don't need an absolute value. As a matter of fact, absolute value would be a mistake. For example, if you have negative 2 and you make a power of 3, the result that you're going to get is going to be negative 8, right? You multiply negative 2 times negative 2 times negative 2, that's negative 8. So now you can take the third, or we sometimes call cube root of negative 8. First of all, you can see that I don't have any requirement for this number under this special notation to be non-negative. It could be negative, so I have actually negative 1, negative 8. And the result of that is going to be simply what number there will be whose cube negative 8 would be. Well, negative 2, there's nothing else, right? Not among real numbers that you could find. So that's it. So when power is odd, or when the index of a radical is odd, you have no problem. Okay? You can remember that. When the index is odd, when the power is odd, no problem. So you don't have to remember anything special about it. It's just straightforward reversal. But when n is even, you have to remember that this guy, under this special notation, this number must be non-negative. And the result must be non-negative. Okay? So if you can remember that, great. Now, I need to put up some names of certain things that are new here. Okay? Some of the stuff is already known to you. When you write something like this, we call this power. We call this guy exponent. Sometimes we abuse language, so we call that power as well. But this guy is just simply a base or a basis. Okay? Now we have something similar for radicals. So when you have radical, then we have also names for this stuff. We call this guy radical. Then we call this guy radicand. You're going to remember that. Radicand. And we're going to call this guy, we're not going to call it exponent, we're going to call it index of radical. And sometimes we'll abuse language, which is simply going to call it radical. This guy. But we should call it index of radical. So that's the notation. Also, there are some conventions that we use. The following convention is known to you. if you make the power of 1, it's as if you don't write anything. That means you just simply write 8. Any number with the power of 1 is just simply that number itself. Okay? Now, if you don't write anything for the index of radical, that doesn't mean 1. It means 2. You gotta remember that. It's a different convention. So here convention, if you don't write anything, it's 1. That's in terms of a power. If you don't write anything, you mean 2. So if you forget here to write anything, and you have something else than 2, you're making a mistake. Because this will be understood as a square root. And again, this guy is even, so of course I'm expecting this one to be non-negative, and I'm expecting the whole thing to turn out to be non-negative. But you gotta remember that even index of a radical, radicand must be non-negative, radical must be non-negative. I'm gonna write that one more time for you to remember it. So make sure you do remember that, because very often people tend to forget that and are making mistakes when that happens. So, if index of a radical, I want to write it down, is even, and we are talking about 2, 4, 6 and so on, we will not use the index of a radical to be 0. We don't have radicals with index 0. We do have a powers with the exponent 0. That will be generally 1, right? You remember that. That's a convention. Now we don't have that for radicals. So you gotta remember that too. Okay, so we're not gonna have an index to be 0. But it could be any other even natural number, 2, 4, whatever. Okay, so if the index of a radical is even, then 2 things happen. You gotta remember that. Radicand must be non-negative. And radical must be non-negative. I'm talking about the whole thing. The result of making a radical has to be non-negative. So radical itself must end up as non-negative. So I stated it already, and now you want to write it down to remember it. Those are requirements. Right? If one of them is broken, you got something wrong. If the first one is broken, you should not be even taking radical. You don't have radical out of that among real numbers. We're going to talk about situation when that might be something else. But among real numbers, we don't have a result if the radicand is non-negative. If the radicand is negative. So if this is broken. If this is not broken, but this is broken, then you made a mistake outright. Okay? So, let me give a couple of examples. They're all examples from the lectures. I'm not making anything particularly new here. If you take a radical of 49, since this is a reversal of power, and I didn't write anything here, I'm thinking about a number whose square, since I didn't write anything here, this is 2, so I'm thinking about reversal of a power that would be a square. This is a square root. I'm looking for a number whose square will be 49. You have 2 choices, either 7 or negative 7. Since we said if the index is even, and the index is even here, the result must be positive. So the result is 7. Okay? I'll give you another one. All right. Now this is a little more difficult one, so I can make it a little nicer. Let's just make it a little simpler, so you don't have to worry about it. Okay. Now you can ask yourself a question: what am I going to multiply with itself to get 9a squared? And the answer to that would be, again, the question I'm asking here is because I have here a square root. Right? The index here is 2. I didn't write it, so that means it's 2. Is this a positive number? Of course it is. 9 is a positive number, and the square of any number is a positive number, or maybe a 0, but it's certainly not negative. So this is not negative. So I can work it out. Now, I'm thinking the next step is what number I'm going to have to multiply with itself to get 9a squared. And the result must be, you should be able to answer that, as 3a. So when you multiply 3a times 3a, you're going to get 9a squared. Okay, you can say, all right, I'm done here. Actually, you're not done here. Because this could be negative number. We didn't say a is positive, we say a squared is positive or non-negative. We don't know what an a is. Since a could be negative, you make sure it isn't. The end result must be non-negative. So you just put an absolute value on a, and you're perfectly fine. Okay? So when you multiply the absolute value of a times the absolute value of a, that's just going to be a squared. You can try it yourself with any number you like. You will see that's going to happen. The absolute value of a times the absolute value of a is just an a squared. Because a squared is always positive, so the absolute value is not anymore needed. Okay? You gotta remember that. Let me give you another example. Nice number, but hard to guess. What could be a third root? So I want to have a third root, of course, because I have a number here that is negative, so even index would not apply here. I would not be able to have that because the radical in case of an even index, this is odd index, in case of an even index cannot be negative. But in case of an odd index, it could be negative. So no problem there. So I'm thinking about what number that would be whose cube is negative 1.331. First of all, that number must be negative, because if you multiply positive times positive times positive, it will be positive. So it must be negative times negative times negative, which is negative. So it's going to be negative. Now I have to think about it, what number that would be. This one has 3 decimals, so that number you're looking for is going to have a 1 decimal, because you multiply decimal, 1 decimal with 1 decimal, it's going to be 2, with 1 decimal, it's going to be 3. And you can start with 1, and you can think about what that second digit would be, or the decimal. You can try 1, 2, 3, 4, 5, 6, 7, 8, 9. And as a matter of fact, you can try 0. Of course, 0 is not going to work, because that will be negative 1 times negative 1 times negative 1, which is of course negative 1. And this is not negative 1. So if you try 1, you'll find out that's the one you're looking for. Okay? So, oh, yeah, I'm saying it's possible to have a lot more work with radical. They are not that easy to find. So I'm guessing you're probably going to use your calculator. There are a couple of rules you can do it without calculator. There's a particular calculation that works without calculator. I'm not going to really bother you with that. And there's another calculation that is worth remembering. It's called mechanics rule, and you're going to learn about it in calculus. So you will learn in calculus a way to find a radical really fast of any number you want, any radical you want. See, that is something calculus can teach you. But there's also another way to do the square root, for example. There's a particular type of routine to do that, but we're not going to go into that. Okay? Now, you have a basic properties with radicals that you need to know. So there are certain properties, just like with powers. They're actually exactly the properties inherited from powers. So the radical is reversible power, so the properties are inherited. This is one of them. If you take a square root of a square, you will end up with the number you started with. Oh, well, okay. It has to have an absolute value, because I don't know what I started with, negative or positive. I know I had to end up with a non-negative number, because radical with an even index has to be non-negative. So we don't write that again, but we mean to. Okay? So the story goes that this is the case when n is even. In any other case, it's just simply a. Any other case would be odd, of course. Right? That's one thing to remember. Another thing to remember, if you do it in reverse, so I'm doing this in reverse. Let's try with 2 first. So I'm doing this in reverse. What am I saying here? First I made a power, then I make a radical. Here, first I'm making radical, then I make a power. Right? Power first, radical second. Radical first, power second. The result is again a. Now in here, I'm not going to write anything special about the a, because I assume here that a is positive. If it isn't, I wouldn't be able to have a radical here, so that would end up with nothing. Okay? This also works for any other radical. If you make an nth power, then you take the nth radical, you end up with what you started with. I might want to write it in the parentheses just in case, if you need to be reminded that a radicand must be non-negative if n is even. And you need to remember that. Right? When again, this is going back again to the stuff I already mentioned. If the index of a radical is even, then the radicand must be non-negative, and the radical itself must be non-negative. It's kind of easy to remember. So this is the first property to remember. When you apply the radical and power in succession in either order, it's just like you're doing nothing. You start with an a, you square it, you take a square root, just like you started with a. One caveat, of course, again, the end result of an even radical must be non-negative. Okay? If you do that in reverse, if you start with the power first and then radical, so that will be power first and then a radical, or a radical first and then a power, sorry. I I wrote the same thing again. I should write like that. Right? So if you write it in reverse, you get the radical first. That's what I meant to write. If you have a radical first and then you make a power, you end up with the same thing you started with. Radicand. A must be non-negative. So this is the rule number 1. You want to remember that. The rule is, it's easy to remember this way. If you do a radical and a power that are reversal to each other, in either order, it's like you're doing nothing. We're wanting to remember, if you're dealing with an even radical, you must be getting, the output of a radical must be non-negative. And the radicand, whatever is under that radical notation, also must be non-negative. So that's the cover to remember. If you don't have that, you can use an absolute value to have it, like I did here. Okay, so that's the first rule. You will see that rule very often, many times. So I say like this. Let's get the radical of 81x squared. Okay. Now it's very easy to see that 81x squared is a square of 9x. And now you have to do the radical of that, right? So now you use this rule I just mentioned. You have a square and then you have a square root. So it's like you have nothing done. You can just simply write what you have in the very beginning. So before you make a square, you have a 9x, and then you make a radical. So before you make a square, that's the beginning 9x, you can just simply write 9x. With that caveat we mentioned, this must be under the absolute value because x could be negative, so we want to make sure that that is not the end result. So if this is negative, we have 9 times negative is going to be something negative. You cannot have that, right? Okay, let me mention the second property. So the second property of radicals is that you can distribute the radical onto factors. So here is the rule for you. You take a radical, which is square root of anything, and you have two factors like a and b. You can distribute the radical onto the first one and then onto the second one, and then you can multiply. This is the scope of radical. Some people write like that to make sure that you know exactly where it ends. So what do we have here? We have a product of two factors, and then we have radical. Here we have radical first, or each one of them separately, and then the product. So you can reverse the order of multiplication and radical. That's perfectly okay. Again, I have to point this out, so you gotta remember this. If this guy is even, then this must be non-negative. This must be non-negative. Otherwise you're gonna have an even and negative. You cannot have that. This must be non-negative, because otherwise again you would have an even and negative, and you cannot have that. So you gotta remember that. So there is a little caveat here. You need to make sure you remember that. If n is odd, no problem. Okay? Now how do you use that? Here is an example. Just moments ago I have this radical of 9x squared. Factor, 9 times x squared. So you can do the radical of 9 times a radical of x squared, and now it becomes simpler. Radical of 9 of course is 3, and radical of x squared is an x with the absolute value. Okay. absolute value again, because you cannot have this negative. So if x is negative, make sure that you put an absolute value so you don't get it negative. You keep the same absolute value, but sign cannot be negative. So that's the application of this rule. Let me show you mistakes people make. This is often mistakes lots of my students will make. So I'm warning you about this because I want you to do this kind of mistake. 9 plus x a squared. Let's say like a. Could I use x? I don't know. A is fine. So lots of people are gonna do, oh, okay, square, square, 9, and maybe I should write 4 because it looks too similar. So let's put 4 here just for a second. So square, square. Let's just write like this. 4 plus a squared. And then I have, of course, the radical of 4 is 2 and radical of a is a. And now I'm going to be real smart. I'm going to put here an absolute value because I know that a could be negative, so make sure that a is not negative. Well, unfortunately, this is an error here. Okay? And there is a problem, of course, that this rule is not applicable. What is this about? Factors. A and B are factors. These guys are not factors, they are terms. So this is not applicable on terms. This rule is not applicable on terms. It's applicable on factors only. Factor. So if A and B are terms, then you could think like you might have a rule like this, but you don't. There is no rule like that. Okay? And if you need any more convincing, choose A to be 2. If A is 2, you will have here radical of 4 plus 2 squared, which is 4. So you get 4 plus 4, which is 8. And on this side, you will have radical of 4 plus a squared. 2 squared would be another 4. So this is 2, and this is 2. So you get 4 here, and radical of 8 is not 4. Because when you square 4, you get 16, not 8. That shows you that this and this is not equal. When a is equal to, it's not equal. You can try any other number, it will not be equal. Well, if you try 0 for an a, then it will. But any other number, it won't be equal. So again, you gotta remember that this is a rule that is applicable on factors, not terms. If there's a plus here or plus here, you're making a mistake. Because you're applying a rule that is not there. Okay, you can do with this with more factors. So let's see, I have something like this. Radical 3, 125, x with the power of cube and y with the power of 6. That sounds quite difficult. So now you have to think about it. Is this a cube of something? Actually, don't. You can split it up by using this rule. You can do it at once. Third root of 125 times third root of x cubed times third root of y with the power of 6. You can say, oh, look at this. This one has 2 factors. This one has 3. 1, 2, 3. 1, 2, 3. Is that applicable? Yes, it is. Because you can go 2 by 2. You can say, oh, okay, let's have this as one and this is another. So you're applying this property, and then you can continue. There are 2 here. So you're applying property one more time. In either case, you can do that at once on all 3. So this is like a property applied on steroids. You've seen that before, distributivity applied 2 or 3 times in a row, right? So you can split this onto factors. So I have 3 factors. Number 1, number 2, number 3. Radical of 125. Radical of a cube of x. Radical of 6 powered of y. Now, this is not too hard to figure it out. This is 5. 5 times 5 is 25, times 5 is 125. Oh, by the way, you might want to remember this. When you make a cube of 1, you get 1. When you make a cube of 2, you get 8. When you make a cube of 3, you get 27. Check it out. When you make a cube of 4, you get 64. When you make a cube of 5, you get 125. When you make a cube of 6, you get 216. And I'm not going any further. The next one will be 343. Kind of easy number to remember. 343. That will be cube of 7. But I'm going further. You might want to remember those because you're going to see them often. So this is a cube of 5. Okay? Oh, this is peanuts, right? An x. You say, do I need an absolute value here? No, you don't, because this is not an even radical. The next one, of course, is y squared. Oh, why is that? Y squared times y squared times y squared is y to the power of 6, right? So when you make a power of a cube, you're going to be multiplying whatever is on the power of the inside. I mean, if you make a power of power, right? So you're going to be multiplying. So when you take a radical, you're going to be dividing. 6 divided with 3. 2 multiplied with 3. Radical reverse. 6 divided with 3. 2 multiplied with 3. 6 divided with 3. You're going to remember that, right? Or spend some time thinking. And what do you need? You need some power of y. What power that would be? It's easy to remember. 6 divided by 3. That's it. Done. So this is, again, this rule applicable here. Let's see another rule. The next one actually is not particularly new. It's just simply the special version of number 2. It says, when you are having a radical of quotient, you can also split that into a radical on the top and radical on the bottom. And some of you might be studying statistics next semester, I hope. You will be successful in passing this course, right? Then you're going to often use this. For some reason in statistics, radical comes very often in fractions. So this is one of those things that you're going to have to remember. Okay? And this could be applicable on any radical. So it might be something else than a square root. And again, you have to remember, whenever n is even, this must be non-negative, because it's a radicand of an even radical. This must be non-negative because it's a radicand of an even radical. This must be non-negative because it's a radicand of an even radical. So you got to remember that caveat that always goes into the game here. And of course, this is going to be non-negative because it's the end result of an even radical. This must be non-negative. It's the end result of an even radical. Of course, it cannot be 0 either, right? You can divide with 0. And this must be non-negative. So this is in case when you have an n positive. You just have to even. You just have to remember, anytime you have a radical, index of a radical, even, the stuff inside must be non-negative and the result must be non-negative. You can remember that you can always adjust it, use some absolute value. If this turns out to be negative, you could just say undefined. I can't do it. It's just simply not possible. Okay. So how do you use that? Well, sometimes you get this complicated stuff that you need to work out with. So example here, I have a square to be taken off something like this. Okay? I sometimes have students just going to cancel 4 and 4. Ooh, and I go forward. Now you cannot do that, right? Because this is the index of a power, or should we say exponent, and this is a factor. So this is not a common factor. One of them is not a factor, this guy. So you cannot do that. But you can use this rule. So what does the rule say? You can split the radical on the top and bottom. So you have the top and you have the bottom. And you're perfectly fine doing that. You can clearly see this stuff is still positive. The square is positive, 4 is positive, product is positive. This is a fourth power. Is also positive. No problem here at all. And on the top, we have done this already today. I forgot whether did I do that with X or with A, but in either case, it's the same story, only with different label. 2x absolute value. Again, we don't know whether X is positive or negative, so to make sure you get the end result to be positive, just put an absolute value on X. You don't need to put it on 2 because, of course, it's positive. And down there, again, what's here? 2. 4 divided by 2. Y squared. Right? You don't write 2 here. If you don't write, then it's a square root. Like you say, oh, how about absolute value here? You don't need that because the y squared is already non-negative. And of course, we are assuming also it's to make sense cannot be 0 because if we have this guy 0, then all of this doesn't make any sense. So this is how we use it. Let me give you another example. This is, if you ever get to calculus, this is what I get in calculus very often. So people make mistakes even in calculus if they didn't learn radicals properly. This kind of stuff pops up in calculus. Okay, so you can say, oh great, let me just do that property. I have this property here, so I have a fraction, numerator, denominator. It says this property, you can split the radical into numerator and denominator. You can distribute it onto numerator and denominator. So I get a top. So far, so good. Right? But denominator is really not that hard. I mean, you can also further split this, right? You can use the previous rule that says you can now chop this further and you get this. And now you have one more step to go. This one is square root of 25 is 5. And this is the same story we had moments ago, 4 divided by 2. Again, there is 2 here, 4 divided by 2 is 2. So you get squared. Square y squared, you're going to get a 4th power y, right? And again, no need for any absolute value here. What about the top? And this is where I get people making mistakes. Making often mistakes. Sometimes I get people doing like this. X plus minus and then don't know what to do with this guy, so let's just take the radical of 4, we get 2x and then radical of this one plus 2. And like I'm done here. You might as well write x minus 2x, which is going to be negative x, right? But this is not so. Okay? Because you cannot distribute the radical onto terms. You can only do that on factors. Distributing or, splitting radical onto terms is a mistake. Again, the property is not there that would let you do this. There is no property that you can use here for justification. So what do you need to do here? You need to find out whether this guy is a square. And it is. It's a square of x minus 2. That's a special product. Square of this guy, x squared. Square of this guy, 4. And what should be in the middle? This one times 2. That's a special product. Square of difference. So this time this one, this guy times this guy is 2x times 2 is 4x with a minus as it's supposed to be. So that's what you have. This is identical. This stuff here and this stuff here is identical. This is equal to this by a way of a special product that we call a square of difference. Now you can proceed. square root, like you didn't do anything. Okay? Now if you're in a calculus and you did all of this, good work, good thinking, wrong result. Why? We don't know what that x minus 2 is. It could be negative. Because x could be, I don't know, 1. 1 minus 2 is negative 1. Or x could be negative and you get even bigger negative number. So, to make sure that the end result, look at this is a even radical. The end result must be non-negative. Down there is non-negative, non-negative. This must be non-negative too. Because if it's negative, you're dividing negative with positive, which is negative. So to avoid that, you just put an absolute value. And you're perfectly okay. Okay? Anytime you have an even index, always put an asterisk somewhere on your notes. The end result must be non-negative. Okay? One more property. Nothing special. Property number 4. When you do power of a power, you multiply the powers, right? The exponents. What do you do when you have the radical of a radical? So this radical has an A and this outside one has everything underneath. Easy. No any problem at all. You can remember this is the same rule like for the powers. You just simply multiply the indices. Index n, index m, multiply, and you have a single radical. So you have two radicals, one after another. You have one radical at the end. And the index is just simply a product of the two indices you have. How do you use that? I don't know. There are not very often reasons for this property. It is worth remembering because sometimes you do have a reason for this property. I'll give you one. So let's say I want to make a 6th root of 64. You say, what the heck? Who knows what that is? I don't know. I don't know. Here is the, for cubes, I don't know what 6 powers. But you do know that 64 is a square of 8. I hope you do know that. So you can say this is equal to a cube of a square root. Cube root of a square root of 64. Why? Because this property says so. When you have a cube of a square root, you multiply this 2, you get 6. So this is just a reversal. What I have here is here. 3 times 2. What I have here is here. 3, 2. And A is of course 64, right? So now you know. Radical square root of 64 is 8. And now you need to make the cube root of 8. And that will be 2. Alright? So I'll just use this property. Not a particularly revealing, but good enough. Okay? So that's the place I want to use it. Okay, what else we do with radicals? So far we were extracting them, right? Sometimes people say, I extracted the root, all right? It's like a tooth. Well, we do everything else we do with numbers, which means we add them, we subtract them, we divide them, we multiply them, and we make special products with them. So how do you add them? You can add radicals that have the same index and the same radicand. That's important. You can only add radicals, they have the same index, the same radicand. 2, 2, 7, 7. That can be done. So you have 3 of them and 2 of them, which means you're going to apply the distributivity, which is it's a fruit analogy. Distributivity is a fruit analogy, so you can simply use it here. 3 apples plus 2 apples is 5 apples. That's a distributivity. This is a common factors, radical 7. You can extract it and you add 3 plus 2. So distributivity says 3 plus 2 times radical 7, right? You multiply this, and you have this multiplication 3 times radical 7, this multiplication 2 times radical 7. So that's the distributivity in progress, but then of course you can remember the fruit analogy. 3 apples, 2 apples, 5 apples. But that can only be done if you have the same index and the same radicand. So you gotta remember this. Sometimes people do this stuff. Okay? Alright, 3 radical 7 plus 2 radical 7, 5 radical 7. Mistake. Because this one is a cube. So you have a square root and a cube root, and you end up with a square root. Where did the cube go? Use your calculator. Your calculator will tell you that this side here is not the same as this side here. So that's a mistake. Again, this is not allowed because there is no distributivity that can be used here. This guy and this guy are not the same, so they're not common factors. And distributivity cannot be applicable here. So which means this is a mistake. You could add radicals only when they are identical, which means you have to have the same index and the same radicand. You gotta remember that. Okay? So I have here something that is a little more complicated. Like I want to subtract radical 20 minus, I'm using one example in the lecture, which is not exactly the one that I wrote in the lecture, but I want to do this. Okay? So you can say, yeah, great, but I can do nothing here. Is it so? I'm gonna make it a little more. I'm gonna make here, I don't know, 60, just for fun of it. Yeah, don't like that either. I'm gonna make 75. Yeah, don't like that either. Let me see. Oh, you know what? I can just keep it 20. I'm trying to adjust it to look it nice because I don't want to get the end result I don't like, but it's okay. So again, you say, what am I going to do here? I can do nothing because radicand is 20, radicand is 5. They're different radicands. Yeah, the index is 2, but I don't have the same radicand. So which means if you follow my previous discussion, you could not add or subtract radicals that are not identical because they are different radicals. But you could work this out a little more. So what you have here is 4 times 5. That's your 20. And then you can split. There is a property that says factor, 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 factor. So instead of having a radical of product, I have product of radicals, which is okay, right? That was the property number 2. And what we have now, this is 2. And now you have the fruit analogy. 2 minus 3 is -1. What? Bananas, right? 2 bananas minus 3 bananas is negative banana. I'm getting tired of talking about apples and oranges all the time. Okay, so that's okay. So again, you could not subtract radicals that are different, but you could modify this one until you get the radical that is identical to this one here. And then all of a sudden you can do it. So sometimes those tricks are around. You might be able to do that. So let me show you another one. So again, you're gonna end up with something like that. You're gonna see that in your homeworks. Right, so you get 4 x cubed y, and there is a radical 2 here, right? Didn't write it nicely, so I'm going to write it like that. This doesn't cover 4. 4 is just a factor on outside. This is somehow traditional notation people use. And then I want to subtract 2 radical xy. Okay? And again, you have 2 radicals. Radical, they're not identical because even though they have the same index, 2, the radicand is different than this one. So this one is x cubed y, this one is xy. You say, all right, I can do nothing here. As a matter of fact, you could do something. So you have x squared xy. The guiding light should be, an xy. I want an xy to have here. You have a square and xy. And now you have 2 factors, 1, 2. So you can split the radical. I'm calling it splitting, but you can say distributing, right? It's kind of like a nicer Latin word to it. All right? And now, square root. Like you did nothing. And again, I'm remembering here that I have even index. So this cannot be just an x. X could be negative. Absolute value of x. So now I have xy minus 2 times xy. So I wonder what am I going to do next? Well, a common factor. Look at that here. 1, 2, 3. 1, 2. Common factor. Good old story. So you have the common factor out, distributivity, and you're adding 4 absolute value of x minus 2. But technically I'm subtracting, right? You can always think about adding negative. Common factor. I'm applying distributivity here. It's a little bit harder to see this as a fruit analogy because I don't think you can think about it. 4 absolute value of apples. Doesn't make any sense, right? But I'm still using distributivity here. No need for fruit analogy, it's just distributivity. Okay? So that's about adding and subtracting. So sometimes, if you don't have identical radicals, you will have to adjust them. If you cannot, until you have identical radical, then you're just simply not going to be able to add them. And that's perfectly okay if that is so. About multiplication of radicals. Well, that goes by the rules. So here's my example. I have radical 3 times radical 27. This is the square root in both cases. So the property number 2 says that you can write this as a single radical 3 times 27. Why? Because these are factors. So a radical of a product of 2 factors is equal to the product of 2 radicals separately on those factors. So this is 81, and I think you know that 9 squared is 81. So you're done. And I know sometimes people go and use a calculator here. 1.73 something on calculator. This one turns out to be, I don't know, 3 point something. Oh, excuse me, 5 point something. So maybe if I get a good calculator, I end up with 9. Maybe on I don't end up with 9, but I'm going to end up with 8.997 or something. I'm going to write it down. There's going to be a mistake, of course, because this is really 9, not something close to 9. So if you start approximating, you're running a chance of making a mistake here. Right? So again, I'm applying rule number 2, properties of radicals. So that is quite available for you, so you can do this. One more with something you will not be able to find on your calculator. Okay, how are you going to multiply that? Well, distributivity works again. This is a number, this is a number, this is a number. Distributivity says you multiply this and this and this and this. So you got a radical squared. You multiply the same thing with itself, right? And the second one, you have negative 5 times radical a. We usually put the concrete number forward and then the radical backwards. You can say radical a times 5, but we rather write 5 times radical a because here is the reason. If you write like that, then people might get confused. What do I have here? Is that a with the subscript 5, or is an a inside, or who knows? So that's a little bit of a problem. So avoid those kind of problems. You just write like that. There's no any confusion here. 5 is multiplied with radical a. So you're almost done. You just have to write here an a, right? And here you got 5 radical a. So you can say, do I need the absolute value here? Actually, you don't, because this one is assumed to be non-negative, because otherwise radical would not be possible. So you don't need an absolute value here. It's assumed that a is non-negative here. So if a is negative, you can't even start with this, right? Because that would be negative, and you have an even radical, so you cannot have anything here. Okay, let me give you one more example. Okay, if you have this in some calculus or pre-calculus, you might get confused with that. Actually, it's very simple stuff. You have one number plus another number and the same number minus another number. So we know that this is a form, special product. How is that going to work out? It's going to be the first number squared minus the second number squared. First number squared minus the second number squared is the same as first minus second time first plus second. So if you can recognize the form, you spare yourself from excessive multiplication. Yeah, you can certainly do that by FOIL. This time this time this, this time this time this, and then you're going to work it out. If you don't make any mistake, you're going to end up with the same thing at the end. But so this is a little faster. So now I have radical, 5 times radical squared it. You multiply 5 times radical a times 5 times radical a is 25a. Right? And this one is a square of radical b, which is just b. Done. Peanuts. Easy stuff. Or a different form. Radical 3 minus radical 2 square. What do you do here? I know you're going to try to use a calculator, right? When you try to use a calculator, you're going to get an approximation. You're going to have decimals, and I have to tell you that you're going to make a mistake if you do that, because the decimals are not the answers here. Let me try my calculator. So with my calculator, I'm lazy to do the job, so I say radical 3, and my calculator has a radical. So I got something, 1.73205, blah blah blah, minus, and now I have a 2 with the radical and I get the answer when I subtract, and then I have to make a square, and I get something like a, alright, 1.0, oh, looks like I don't have even 1, I just have the point. That's what my calculator says, and there's more there, so it's another 0 and so on. So you're going to write like that, and you're going to say, okay, I have it. No, you don't. This is approximately equal. So when we say this, we mean identically equal. Okay? So you write 2 plus 2, you mean 4. You don't mean 4.01. Okay? So again, you gotta remember that. If there is a sign here, so did you have to write something here that is like this but without parentheses? This one will not be the one, because that is not identically equal to this one. This is a result of a calculator that gives you an approximation. So what do you need to have? Well, you just need to do the algebra. Square of this guy, square of difference. This time 2. And then square of this guy. Next step. Square of radical 3 is 3. This is 3 times 2, 6. So you have, okay, this is 2 times 3, right? Or 3 times 2. So you get the radical that splits into factors, you get radical 3 times radical 2. So this is identical to, equal to this. And 2 and 2, of course, stays. This is 2. 3 and 2 can be added, you get 5. This is the correct result. You can say, oh, that doesn't look nice. Yeah, it doesn't look nice, but it doesn't have parentheses. If your goal was to simplify, to get rid of parentheses, we did it. This is identically equal to that. This doesn't look nice? Sure, because this is irrational number. This is not a fraction. You cannot write this any nicer than this. This is the best way you can write this number. What is this number? There's some number whose square 6 is doubled and subtracted from 5. That's what you have here. It's not a nice number. It's not a rational number. It's not a fraction. It's definitely not an integer. 1, 2, 3, 4, 5. It's something else. But it's a perfectly good number. And this is the simplest way you can write it. There is no any other way you can write this better than this. So you gotta remember that sometimes, yes, you do have to write numbers the way they are. Because if you want to keep it equal, which you do want to, because you have this sign that is not a sign of approximation, it's sign of equal. And then you have to do this. Okay. Rationalization of radicals or fractions with radical. This is very often business in calculus and pre-calculus. So you have radical 2 and one is divided with radical 2. What do you do with that? Well, it's difficult to get the radical 2. Radical 2, you can get an approximation 1.41 42 da da da, and then you have to divide 1 with that, which is really nasty division because the divisor is really complicated. So that's a bit of a problem. So it's nicer not to have radical in the denominator. So how do you accomplish not to have a radical in the denominator? This is the way. First of all, you can examine that this holds because this is 1. And when you multiply a number with 1, it stays the same. So I'm not violating anything here. Okay, what's the trick here? Well, we multiply fraction, we multiply the top, 1 times radical 2, and we multiply the bottom. Radical 2 times radical 2 is 2. this is the number whose square 2 is. So when you multiply the number with itself, it's 2, right? So, hey, I came from this to this. I have here 2 in denominator. It's not anymore radical. So it's easier to divide with 2, right? Think about it. Any decimal number is much easier to divide with 2 than with radical 2. So this is easier to work with. Yeah, you still have radical, of course. Radical didn't disappear. So here it was in denominator, now it's in denominator. So, yeah, it will stay there. Okay? Now here's another one. Now this is a particularly nasty thing to get in calculus. It's very difficult to write, work with the radical expression in denominator in calculus. You'll see that if you get that. Okay? So you can ask yourself, how do I do this now? You can say, well, you know what, I'm going to do the same thing as before. If I do this, I'm not doing anything special, I'm multiplying with 1. So I end up with 3 radical x. And down there I have to square this and I get the x. And I'm done. Actually, no, it's a mistake. Because if you multiply this with both of them, you're going to have to multiply with this one too. So you're actually going to get a radical x. So you didn't accomplish anything. You get something that was before even worse now. And now you have radical up and down. So this is not going to work. So the same idea I was using moments ago is not going to work. So how is this going to work? You have to think like this. I need to square both. I need to square this. But I can't just square this because if I multiply with this guy, I'm going to square this, but I'm going to get this radical here. So I have a problem. But you can do with this. I'm going to let you think about it. Why are we doing exactly this? First of all, this is again 1. It's 1 again, because it's the same number divided with itself. Alright? So the story here is that I'm going to use the good old stuff here. A minus B times A plus B, which is A squared minus B squared. You see? I'm going to square this guy, which is my B. B. A minus B, A is 1. A plus B. A minus B, A minus B. A plus B, A plus B. And then I square them both. And all of a sudden, radical disappears. So that's the goal. You can remember this. Okay? Okay? Now if I have here plus, I would do exactly the opposite. I have minus here. And again I have a square. On the top I don't. So I have 3 times 1, 3 times this. You have to multiply 3 with both of this, right? 3 times 1, 3 times this. Okay? That's the top. The bottom is A plus B, A minus B. A squared, 1 squared, minus square of radical x. Fantastic. I got rid of radical in denominator. I don't have it anymore. I have it in the numerator again. The goal of rationalization. So this is rationalizing denominator. Two examples, this and this one, is to get rid of the radical in denominator. You will not get rid of radical. Just don't disappear like that. It's like a cockroach. You hit it somewhere and it pops up on another place. It stays around. But you don't have it in denominator anymore. You can also rationalize numerator. This is not very often done, but you can certainly do that. And sometimes it does happen. So sometimes we do have rationalization of the numerator. But in general, we usually have rationalization of the denominator because this is where the problem is more often. Okay? There are a couple more examples in the lecture. I suggest you to read this. Okay? Now, about the equations with radicals. So you do have equations with radicals. You gotta remember that the equations with radical is the same story, not the same, but similar story to the equations with rational expression. You might get extraneous solutions. You might get solutions that are actually not solutions. Some stuff is relatively easy, like this. I'm always surprised how people get in trouble with a problem like that. It's a very easy problem, actually. So, what do we want here? Solve this. Find what x makes this true. Anytime you run into a situation and you see something you have never seen before, you always have to think about where is your problem. Okay? Now, this is a radical. You have never seen before radical, not in my class at least. You have never seen before in my class that you have a radical in an equation, but now you do. So that's your problem, radical. Everything else you've seen before. You've seen numbers and equations before. You did not see radical in an equation. So, isolate the radical. How do you do that? Subtract 2. So you're subtracting 2 and you get the radical of x plus 9 equal 2. How hard is that? So you subtract 2 from the left side, you got this guy gone. Subtract 2 from this side, you get 2. And now you have a radical isolated. It's a single radical on this side here. Isolated radical. What's the next step? We're going to have to think about it. What number there is whose radical 2 is? Well, that's 4. Some people say, oh, you square both sides. Yeah, you can do that, but that's a little bit of a problem. I'll show you later. You just have to think. I am taking a radical of some number, I'm getting 2. What could that possibly be? 4. And then you're done. X must be negative 5 because you have to add something to 9 to get 4. That must be negative 5. You're done. That's your solution. Perfectly fine. Plug it in to make sure that it works. It should work in the original equation, right? It's a check. If you have that done incorrectly, it's not going to work. Okay? Let me give you another one. Now the one with the problem. X plus 7, and I have radical minus x. Everything so far so good, equal 5. Right? Alright, again, I want to get radical isolated. Because again, you think about it. What's the news here? I've seen equations with x. I haven't seen equations with x involving radical. So, okay, isolate. Add x. So I'm adding x to both sides. So I'm getting radical of x plus 7. This one is gone when I add x. On the other side, I have 5 plus x. So far, so good. Now, you're going to have to think about it, what the number is going to be whose radical is going to be 5 plus x. And you're going to say, of course, I have no idea. Yeah, okay. Let's square both sides. So what we are doing here, we are squaring both sides. Left side and the right side. And now you're going to have to remember this. That was never in any of those rules that you could do. We didn't say you can square both sides and keep the same solutions. We didn't say that. Okay? Here's a trick. First of all, you have to put an asterisk here because this is not something we listed as a possibility to do. It might not keep equivalence. Might change the truth of the equation. If it's true, 2 is equal to, when you square it, stays equal. If it's not true, negative 2 is not equal to. When you square it, it becomes equal. That's why we didn't list that, because squaring both sides of the equation could produce truth of something that was totally false. If it's true, stays true. If it's not true, became true. So you're gonna have to remember that. You're doing something that could add more truth to what you had before. The good thing is never loses truth, right? If it's true, stays true. But it could add truth. So just like with rational equations with rational expressions, we said there is a possibility to end up with an extra solution, an extraneous solution, something that is really not a solution. The same thing here. You could get more truth than what you started with. So let's work it out. You square this side, you get an x plus 7, right? No doubt about that. You have radical square root. If you square it, you just get what you have started with. On this side, you need to square this. So it's going to be 5 plus x times 5 plus x. You can work this out. It's not that difficult. You're going to get this. Some of you remember the special product. That is a special product. If you don't remember special product, do the FOIL. 5 plus x times 5 plus x, scrap paper, you're going to end up with exactly what I have there. Now, you say, what the heck am I going to do now? Well, now you're going to use the zero product property. This is polynomial on both sides. You just need to simplify this and use zero product property. I'm going to subtract all of that. So I get 0. Subtracting x, I get 9x. Subtracting 7, I get 18. And here I get an x squared. Beautiful. Okay, I know you don't like to see it that way, so I'm going to put 18 on the last place and x squared on the first place, because that will be the standard format. And now you take a look at what you have. That over there is something that you need to turn into a product. And that will be, I guess, 3 and 6. So factorization, of course, zero product property. 0, you got 0, but then once you get 0, you need a product, so you need to use factorization. So you got x plus 3, x plus 6, not really difficult. And now you have a zero product property that says one solution is -3. This is when this guy is equal to 0. You know, this might be 0, so the x is -3. And the other solution, the number 2, would be -6, because -6 makes this 0, and this is true again. So you can say, oh, perfectly beautiful, I'm done, I'm gone, and I have both solutions, I'm done. You're not done yet. Now what's the problem? Well, the problem is that one of them will work, so you can have to check it, and one of them won't. All right? So the best way is to check that in original equations, just to make sure that it holds. -3, if you plug -3 here, you got 4, 7 minus 3. Radical 4 is 2. 2 from this guy. -3 is 3. 2 and 3 is 5. Oh, beautiful. This one is perfectly fine. The second one. You plug -6 here, you will get radical 1. I should do that on a separate piece of paper, right? So, like this is my scrap paper here. I plug in -6 here, I got radical 1, 7 minus 6, minus -6 here, instead of x, -6, instead of x, equal 5. Well, this is not equal, because this is 1, and this is 6. And 7 is not equal 5. So what the heck happened? Well, once I square it, it becomes equal here. You can try here. -6, 7 minus 6 is 1. -6 here is 36. -6 here is -60. So 36 minus 60 is 24. 25 minus 24 is 1. 1 is equal 1. Ah! At this point, -6 become solution. Here, it isn't. Negative 6 plus 7 is 7 minus 6 is 1. Radical is 1. And here you have 5 plus negative 6, which is negative 1. 1 equal negative 1. That's not true. But once you square it, 1 equal negative 1 becomes 1 equal 1. So it becomes true here. This is not a solution. This is extraneous solution. So after checking this, in the original equation, I realize that this is not a solution. This is. So again, at this point, what can you do with the equation? You can either subtract the same number to both sides. You can multiply or divide with the same non-zero number, both sides. And you can replace anything with something that is identically equal, like 2x minus x is x. You can replace 2x minus x with x. So those three things you can do. Nobody says you can square both sides. So when you square both sides, you gotta remember that you might be adding truth. You might start it with 3 is equal 4. When you square it, 9 is equal 16. False stays false. But it could also be 3 is equal negative 3. And when you square it, it becomes 9 equal 9. The false became true. That's what happened here. With this negative 6, this is 1, negative 1. Not true. But when you square it, it becomes 1, 1. True. So watch out. Yeah, you can do this, but you need to check the solution. This is the same story we have a rational expression. You can have extraneous solutions, solutions that are not solutions all the way up, but they become somewhere on the way. Here. On the way, when you were doing something that was not one of those three things you can do with equations. You have to always remember, you're doing something that is not one of those three things, you have to check what you're doing. Okay? More. Historically, we use radical notation that is from 500-600 years ago. And we don't really like to use in some better mathematics or higher mathematics, we prefer to use power notation. This is often called rational notation, so rational exponents. That's basically a power notation. So radical can be written as a power notation. What does that mean? So when you have radical a, so this is the square root of a, you can also write it this way. A with the power. This is now a power notation. But this is not the power that you ever seen before. Before we only had integers, like positive or negative, could also be 0, but we never have fractions. Now you have fractions. So you have this guy here, which is 2, and now becomes a power, but upside down. Okay? That's a lot more convenient. A lot more convenient to have it like that. Because all of the all of the radical rules I have, 1, 2, 3, 4, are just exponential rules about powers. Okay? And again, if you have something like this, it means 3 is your regular cube, and 2 means your regular square root, because it's upside down. So that's a convention. Very interesting, right? You can read it in a couple of different ways. You can read it like this. This is a with a power of 1/2, and then cube. And you multiply this, you get 3/2. The power rule holds. And so you have here radical a cubed. You can also read it this way. It's an a cubed with a power of 1/2. And again, if we multiply power to power, you got 3/2. So you got the square root of a cube. You can do power and radical in the any order, as long as you follow the procedure that says in this particular case this must be non-negative, right? Because it's a even radical. So this becomes very, very nice. Now remember, I had those rules before. I had the rules that says like this: a with the radical n, and then you have radical m. So I said this is now a with m times n. Oh, excuse me. Radical m times n, and I listed that as a rule number 4. This is really nothing special, because it's just straightforward power rule. But how is that a power rule? Here, this is a with a power of 1 over n, and then on the outside you have power of 1 over m, mth root, nth root. So we know that with exponents you just multiply the two. Which is radical index. You actually don't need any, don't have any good reason to keep this notation around. You can just simply use the power notation. Anytime you have radical, it's just simply a power with a radical index of radical in denominator. And all of the rules that you know about powers hold. Now why is that? That would be in something, in a course we call real analysis, some serious mathematics, so we're not going there. But the idea is very simple. So again, you have a cube root of a, you can just simply write this way. Alright? So you have some of those properties that we had before. You say if you have a cube root of a cube, that would be equal to, of course, a, right? We said it before. If you do the power and the radical with the reverse of their power, you just end up like doing nothing. Well, you can see it here. This is the a with the power of cube, and this is the power of 1/3, which is a multiply 3/3, which is a with the power of 1, but then 1 we don't write, so that's it. Huh. Okay? So this is, again, this is the property number 1 for the radicals, but it's really nothing special. It's already known to us from our rules. Let me give you another one. So this is how you can simplify some stuff. I have here radical 6 had to be multiplied with the radical 6 cube, which is also added with a radical 6. So let's simplify this. Holy Moses, right? I mean, hard to read what that is. So you're probably going to try to do the calculator stuff, which is going to be a mistake. Don't do that. Here you go. Let's just write everything with the rational exponents, means fractions, right? And the power notation. Fractions as exponents. This is 1/2. This is 3/2. Again, 3 is your regular numerator. This goes in the denominator. 2. This one, square root. 2, denominator. And I have everything in power notation. Now work it out. Multiply, multiply. That's the distributivity, good old story, right? So you got 1/2 plus 3/2. When you multiply this time this, you're gonna just add these two guys. And the second one is gonna multiply this and this. You're gonna add 1/2 plus 1/2. 1/2 and 1/2. I should say radical 6 power 1/2. Power 1/2. You multiply, you add these two. Those are power rules, nothing special. So what I have here, 1/2 plus this half is 2. 1/2 plus 1/2 is 1. I have 42. 36 plus 6 peanuts. Okay, this rational exponent, or the power notation we use for radical, is a lot more convenient. So you could ask questions, why don't we use that all over the place? Why would you simply use this outdated notation like this? What does that mean, actually? Like you're pulling some radical. This is having a root in the ground, so you somehow have to pull that radical. Radix is Latin for root. I don't know. Traditionally, we use that. It's tradition. Sometimes people hold to traditions, right? Why do people wear, ties? I don't know. I never wear ties. Huh? Tradition. In the past, they needed because they didn't have buttons or something. I don't know. So they just were using it. But now we don't need that. But we're still using that for a tradition. So this is traditional notation. But the power notation with the rational exponents of fractions, rational exponents of fractions, or just a power notation. Radical could be written in a power notation. It's a lot more convenient. It's easy to work with, and you don't have any more new rules. You just simply have power rules that are from the story about powers. So if you know the story about powers well, you can work this one out too. Okay? Again, you have to do the homeworks here. The homework, number 6, the number, I don't know whether number 16 or something, but it's homework. It's called radical expressions, so homework. And you need to do the homework. They will give you some handle on this. There are plenty of problems there. And you should actually read the lecture and you see more examples in the lecture and go over those examples. If you have any questions, send me an email about it, or drop by the office hours, which are on the Skype, right? Okay, I'm gonna end up this stream, and this is our lecture number 16 done.